for inviting me. Today I'm going to be talking about watermarking for GenAI models. The technical content would be more in the context of LLMs, but I'll motivate the problem in general. So this is based on joint work with my co-authors Jaden, Samesh, Saeed, Mohammed, and Mingwan. And some of the slides have been borrowed from other folks. So thanks to them. Okay, so what's happening in the world that we currently live in? Fake media seems to have taken over our lives. So the first example here is apparently there was a fake media video of Taylor Swift selling Le Creuset cookware. On the more serious side, there was a recent person in New Hampshire who commissioned a robocaller to make calls on behalf of Biden. So it was mimicking Biden's voice, telling voters not to go vote in the primaries. So that's a bigger problem. There's also another bigger problem is what's deep fake Elon Musk. If you go online, you'll find lots of videos of Elon Musk, a lot of them deep fakes, in which he's trying to convince people to invest money in one place or the other. I was reading there was one person who lost $600,000 to a deep fake from Elon Musk. I mean, while we're seeing this proliferation of fake news, the idea of sort of changing things is not new. So the picture that you see on the left is Abraham Lincoln, right? But apparently in the picture, the body is not his. So it was taken from someone else. So even going back to 1865, we have these doctored images. It's another picture of Ulysses Grant, a very famous picture. It's all fabricated, given three other pictures in 1902. So lots of modifications even then. Another interesting example is this of the picture on the left. You see this person's was the head of the police and with Stalin. He didn't like him. He got him executed and got him removed from the picture. So you know, over a period of 80 years, we were kind of doing this modification to images and so on. It was expensive. Someone had to do that. But now very quickly, we've gone using GANs. First, in a very short period, we've gone from computer-generated images, which were really of poor quality, to something which is, you know, almost indistinguishable to the human eye. And we have these images, and they're going all over. And we have these now really powerful text-to-image generation models. You can give a prompt, give a description of what kind of image you like. You get an image. You can say, "I want, you know, the President Biden surfing." You'll get a picture him doing that. There are text-guided image editing tools, so you can take an image, give a prompt, and ask it to change things in a way that to your liking. You get the newer image, which has a modification accordingly. Another example here in terms of affecting elections. This is a fabricated image that was going around. Just one example, the many such pictures of some groups trying to persuade black voters that Trump voters like him. Sorry, black voters like him. I mean, this picture does look doctored. So, you know, you might see a finger is missing on the person in at the leftmost edge. This Trump's hand seems odd. His left hand seems odd. So it might look doctored, but these are all over the place. The elections in India recently, there was all over the place. There were, the first image you see is of a politician sitting in front of a green screen. They made a clone of him so they could simulate him talking to people in sort of a one-to-one conversation to get his message across. So that was happening. The picture below you see is actually a dead politician brought to life using GenAI. So trying to convince his, you know, followers when he was alive to lie. I mean, these might seem bad, but the consequences are of using this sort of misinformation, which is doctored, are really rising. So the leftmost picture you see is an explosion that happened. There was no explosion that happened. It was like a doctored image of an explosion near the Pentagon. And what it did is it sent the market down. So people were scared. They started selling, and the frenzy caused markets to fall. So, real people losing real money. There is a court case that's pending where Elon Musk, someone did something listening to Elon Musk, but his lawyers are claiming that those could potentially be deep fakes. And so he's being asked to testify about it. The opposite party saying, well, this is just, an argument that if everything is, no public personality can now be held accountable because there's enough deep fakes for them. And so you can never trust whether you're, listening to someone real or fake. This picture of Salima Gole got a lot of likes, and this, she wasn't even there at the Met Gala, so that was. There are also serious consequences. This is not completely Gen AI, but bot, so not high tech Gen AI maybe. There was a case where 5 people were killed because they were scared, because other people were scared that they were trying to kidnap a young woman while they had just offered her a biscuit. So this is sort of happened where people were actually killed because of misinformation. And there are other things that are coming up. Blackmail, impersonation, we all know about some of the other examples as well. There's some legitimate use cases as well. So this is a popular Bollywood actor, and he was cloned, and his thing was used in lots of ads. So in multiple languages, probably many he doesn't even know how to speak. They used his clone to advertise local shop owners, the products they were selling, and so on. So some reasonably legitimate use cases as well. And this has not gone unnoticed. So lawmakers everywhere are worried about it. They want steps to be taken. So this is just a small list of the AI laws that have come up recently. This includes the US Biden's executive order. The 3 most significant ones are the Biden's executive order, the EU Artificial Intelligence Act, and the China's initiative. Kind of all these laws are worried about these kinds of problems, and a key requirement they've come up is requiring that any AI generated content be watermarked. So in some form or the other, not necessarily in the same words, they do tend to require something like this. However, a bit of a challenge with these watermarking laws is that there isn't a clear understanding of what the technology is going to deliver. And so, for example, the US law just says, develop guidance for content authentication and watermarking to clearly label AI generated content. In India, the Prime Minister said that AI generated content should have a watermark informing people of its origins. But what properties is the watermark required to satisfy? If it's insecure, is it still good enough? There's nothing like that in the law. So that's a real problem. And so the laws are coming up. People are going to adopt these technologies. So if you're not going to be ready to put in place something that's reasonable, we're going to end up in a situation where we have watermarks which are basically meaningless. So let me kind of try to explain this, like how maybe a layperson would envision what a watermark should satisfy. And we can call it an LLM tuning test. So you could have a setting where there is a interrogator or somebody who's in world 0 talking to the natural distribution. So it's a human person they're talking with, and in world 1 they're talking to the text generated by an LLM, and they're trying to distinguish who among the two sources are they talking to. And this is what one can imagine as sort of like a tuning test, and where the goal is to distinguish, and a watermark should perhaps satisfy this. But there are other requirements that are also relevant, which is, what if we want some kind of a robustness where there's another person sitting in between the computer and the interpreter. So for example, in the setting of a student trying to write an essay for a class, maybe they're trying to use which is not the worst of problems with this, but anyway, one of the issues that are often discussed, where if I'm using a LLM to generate the essay and submitting that in class, maybe I'm also sort of changing it a little bit along the way to hide the fact that I'm using LLM to generate that essay. So there's some need for robustness as well. So there are lots of these requirements that are coming up here, but we don't have a precise. We can't just use the tuning test as a definition here, because we need these other properties as well. Okay, so at a high level, there's kind of two kinds of Gen AI detectors that exist. The ones, for an LLM or more broadly any Gen AI model, that the output of the Gen AI model is going to be different statistically from a human-generated content. Okay? So that's an assumption you can kind of make, that, well, these models, the output distribution is different. If it is indeed the case, then you can run another machine learning model to identify whether maybe it's machine generated or it's human generated. So you can try to distinguish the two. But as these models get better and better, the envision that we think is appropriate is that they're going to get better, and we're not going to have these kind of differences, and we're not going to be able to tell apart human generated content from machine generated content. And so we actually need to change the output distribution of the LLM generated content so that it can be later identified as such. Okay, so that's the world I'm going to kind of live in and focus on for the rest of the talk. As I said, I mean, I'm going to talk about watermarking, but I'm going to focus on watermarking for LLM models. The problem is also interesting and relevant and studied in the context of other Gen AI models, for example, images, but not necessarily by our community, and they don't necessarily have the same theoretical grounding as such. So those are really interesting open problems. So developing watermarks which work in those settings for images and so on would be fantastic. Okay. I mean, you could apply the same theoretical techniques, but not necessarily. The tools haven't really been built, and there are kind of finer attributes which come to play, for example, when you're working with images or videos. So those haven't really been worked out. In terms of watermarking, the idea is, as I mentioned, to change the distribution that's generated. So we're going to embed a statistical test. So for example, if you have a machine-generated text, we want to change the output a little bit so that the watermark can be later detected. We want to avoid false positive. So text that was generated without being watermarked should not be detected as being watermarked. So that's something that we want to avoid. We also want to avoid false negatives. So we don't want to be in a situation where we generated a text with a watermark, but then is later not identified as such. Okay, so we want to avoid these. So these are some natural properties that one would expect, but there are other sort of context-specific properties that are going to be relevant here. The first is that we want the detection in these settings to be easy. So if you have a LLM generating some content, I don't want to have to know the original model parameters or anything about how anything proprietary about how the watermark content was generated. So imagine you have this sort of billion parameter model. That's one additional property that becomes relevant. Another property is that we don't want typically when you have this, if you have on watermark test, you don't want to retrain your model. So it's not, you want to use existing models and then maybe change it to add it. But don't want to have to go back and teach the model. The detection should almost, ideally be with probability 1, I should detect this. Because we're going, or else also interested in robustness. So, someone might we could also, it could also be helpful to have a confidence level. Watermarking should remain robust to small perturbations. So, as I mentioned, we want it to be the case that if you change a few words here and there, for example, the watermark shouldn't suddenly disappear. And finally, this is a property not necessarily covered in the initial work, but the more recent ones, where we want watermarking, the process of watermarking shouldn't degrade the quality of the output that LLM is generating. So for example, let's say you did $1 billion of R&D to have this really awesome model that generates high-level text quality, and suddenly, we cryptographers come and say, no, you need to watermark, and suddenly the quality of the text goes down. That's not going to be acceptable. So that's very critical. Okay. So at this point, with all these properties, a natural question comes to mind is, can't an attacker just rephrase the LLM output to remove the watermark? And maybe I change a few words here and there. And if not, maybe I run another cheaper LLM that maybe rephrases the text. And the answer is yes, you can. And this is where the situation starts becoming tricky. There's this recent paper from Harvard where they show that strong watermarking, where you can make all kinds of modifications where you don't limit the attacker's capabilities, watermarking is not going to be possible. And the same idea where you take the text, rephrase it a little bit, and then rephrase it a little bit, and rephrase it a little bit, as long as till the point the watermark is destroyed, have been demonstrated on some real-world schemes as well. And the algorithm that they present in the paper is exactly that. So this is the impossible result. You start with a initial value y that's watermark perhaps, and that's, you set that to be y prime, and you take y prime, and p is what they call a perturbation oracle. So they're taking the y prime and modifying it a little bit, and they check that in doing that small change, the quality didn't become much worse. Q is what they call a quality oracle. So they take the watermark text, change it a little bit with what they call a perturbation oracle, check that the quality isn't degraded much. If it hasn't, then they run the perturbation oracle again, and they run it a sufficient number of times that any watermark is going to be removed. And it's natural to expect, right? If I keep changing things and the watermark is not removed, then maybe any text is going to have, I'm going to get false positives. Text that wasn't originally watermark is going to get detected as watermark. So that's sort of the core intuition. They have a formal analysis for why this sort of an attack will kind of always works. And kind of in light of this, and we will focus in this talk on trying to embed watermarks that will not be robust to any kinds of changes. We're going to limit attackers' abilities. We're going to focus on settings where the attacker is at least prevented from removing the watermark with those sort of limited amount of changes. Okay, so I'm going to talk about two works. The first one I want to talk about is sort of the early work in this space, which is a secret key scheme. And then I'll talk about the second work that we have, which is a public key scheme. This is from Maryland group. And then the idea here is actually fairly natural, and so it's sort of easy to understand. So I'll start with this. The language model works as follows. So just a reminder for everyone. So let's say you have some text match set on the right. So what the language model does is you give this text to it, and it spits out these. It has a list of words in its dictionary, so to speak. It outputs logic values, which can be translated into probabilities for how likely the next word is to be. So if you write Matt sat on the chair, the next word is likely to be couch with the probability 0.4, or chair with probability 0.3, and so on. What these folks observed is that what you can do is you can partition the words into two categories. So for example, if you ran a hash function, which maybe outputs green with probability gamma and red with probability 1 minus gamma, you can take the last word, the, and the next, the words in the dictionary. So the comma couch, and map it to red or green, depending on whatever probability it outputs, red or green, this hash function. Okay. So in this way, you can partition the words couch, chair, floor, cat, table, and so on into one of the two categories. And their idea is that, well, what we're going to do is we're going to require that the completions are done using the green words and rather than the red ones. Okay. So I have these green words, and the next word, even though couch has a higher probability, I'm going to use the green word chair in the example, and so that's going to be my completion, and this process continues. Okay. To make the process secret key, what you can do is, instead of using a hash function, use a pseudo-random function to do this categorization. Keep in mind here that the pseudo-random function is taking two things as input, the and the next word. So this is the comma couch is red, the comma chair is green. So depending on that, we're getting this partition. So every two words are kind of deciding what the combination. Okay. So now what's going to happen is, if you pick gamma is equal to half, because we are insisting on having green words, we're going to have this text which has which is going to be completely green, right? So you'll generate text which is going to be just green words. And so even if someone modifies a few words, they're going to be substantially more green words than the red words, and then I can detect that without having knowledge to how the model works and anything at all, the parameters. So there is going to be no false negatives for a reasonable threshold. So if I set the threshold to be sufficiently high, so I'm not going to get false negatives, and false positives are also not going to happen, because for a random text that you get anywhere, the probability of a word to be on the green list is exactly half. So every word is going to be on the green list with probability 1/2. So I get this distribution, which is, it's going to have half red words, half green words roughly. So I'm not going to get false positives. The question is, what about robustness? Well, robustness is kind of nice as well. So if the university knows the watermarking rule, so half the words are already green, it needs to change maybe the potential. All the words are kind of green. It needs to make sure that it changes sufficient green ones to red, because it knows what the watermark is. It can figure out, change 25% of the words, because note that one word affects two. It affects its own value and the next value. So it can change those words and destroy the watermark by changing like 1/4 of the words. If the diversity does not know what the watermarking rule is, then it has to go ahead and change maybe 50% of the string too. The challenge, this seems kind of all nice. One challenge that they encounter is that it's not always the case that you're going to have a setting where text has high entropy. So for example, if you have a text that starts with the word Barack, then it's very likely that the next word is going to be Obama. But if Obama for some reason ends up on the red list, then it would be very unnatural to use a lower probability word. So in this case, equals, I mean, this is not going to, this looks bizarre, something's wrong. So to solve this issue, they suggest rather than doing a hard green versus red, they suggest a soft bias. So what we're going to do is, we're not going to insist on using the green words, but we're going to push up the probability of using the green word a little bit. So we're going to couch might still end up getting used, but the probability of chair is now going to be higher than the couch because we've pushed up the probability. So now what this does is, for a human-generated or a random text that's unaware of the watermark, half the words are going to be red, half of the words are going to be green. But in the context of the soft biasing, mostly green words are going to be encountered, and so you can still do a detection. Okay? So you can do an A/B test or things like that to do the detection. So there's some limitations to this work. So the first limitation I'm kind of interested in is that the adversary can learn the watermarking rule to some extent, right? Because you're only using 2 words, you can kind of make a dictionary of which words you used and figure out what's in your green list. And once you have that, I can generate new watermark content. They suggested some ways to avoid this. One way is to, rather than using 1 word, use the last H words in the pseudo-random function. So rather than just using the last word set on the couch, you use like the entire sentence or all these words. They suggested some other ways to make it harder as well. It has some, this mechanism has some complications because if the text is low entropy, then we run into troubles. So they suggested ways to get around that as well. I don't want to get into those, but a critical issue in their scheme to some extent is it's unclear whether someone who just looks at a bunch of watermark text, they cannot independently generate a new watermark text. So that's sort of a limitation. Another limitation is that their construction, when they were working, distortion freeness was not a concept. So the output generation does modify the distribution of the content to some extent. In particular, watermark text is at least distinguishable from unwatermarked text, perhaps. And so this is another limitation for their work. There's other schemes in the secret key setting. We had a invited talk at Crypto last year in this context. I see Miranda here, so they have a work very nice which cleans it up. And they have in their scheme, they also get distortion freeness. But one thing really nice about their work is they have formal definitions. So they're nice to cryptographers' ears. So what I'm going to focus for the rest of the time, the last 15 minutes I have, is on the newer work, which is in the public key setting. So the critical difference in the works that I mentioned so far is that you have to have a secret key to be able to watermark text. So you need to know your secret key, and that gets used in watermarking. And now a challenge is that anytime you have to do the detection, you need the same secret key. So now what that does is it creates this need to, if you want other people to be able to detect, for example, if I'm a teacher in a high school trying to detect, or even a university, and trying to detect if my students are cheating on their essay or something, then I have to go to OpenAI or somebody to do all those detections. So, which is not ideal because they have to run these servers. It would be nice if the detection can be done publicly by anybody who has, let's say, the access to the public key for the watermarking model. Another issue is, imagine an OpenAI model generating a hateful content, right? Maybe something that's not very nice. And someone goes to them and asks, is this watermark? Maybe they would not want it to attest to the fact that it was indeed watermarked because it makes OpenAI look bad. So we can't really hold anybody accountable in a setting if we are using a secret key setting. So this is what motivated our work, where we wanted to be able to plant a watermark using signatures rather than pseudo-random functions. So I'll formalize this setting. It's similar to digital signatures. We're going to have the setup where we have a public key and that generates a public key and secret key. The watermark takes the secret key as input and a prompt for the LLM model. So think of the prompt as, he sat on the. So that's the string, and it outputs the token. So in the case of the way we imagine prompts, there's just maybe the next token, one word being output. Here, I'm going to be interested in a setting where it outputs multiple tokens because you have to embed signatures. It kind of forces our hand for the text to be longer. And then finally, we have this detection algorithm that takes a purported text T star as which is being claimed to be watermark, and the public key is input, and it outputs true or false depending on whether the algorithm thinks it's watermarked or not. There's some requirements similar to what I mentioned earlier. We're going to have a completeness requirement. They're honestly watermarked text as long as they're long enough should be detected. Okay, so it shouldn't be the case that I'm going to define them formally, but we can also require here that if you took a long enough text or took a long enough snippet of that text, that should be detected, right? So maybe I wrote a book, it was all watermarked, and someone picks a page from the book, we should be able to still detect that that page is watermarked. One distortion freeness, like prior work, that watermark texts are indistinguishable from unwatermarked texts. We want soundness and unforgeability, which is sort of similar to this, which wasn't sort of as which is different than prior work in the sense that now we have an attacker who gets access to multiple watermarked texts, and he can see them, observe them, try to glean whatever they can, and they should still not be able to come up with a new one. Finally, we want robustness, that if I have a watermarked text, the attacker that's sort of long enough, and the watermark should not be removable with minimal modification. So just changing a few words here and there shouldn't remove it. So again, I'll formalize that. So just formalizing things, completeness is natural. So if you have setup and watermark takes a prompt and generates a watermark text T, detection algorithm should almost always output true. So it outputs false with negligible probability. And note here that I need some sufficient length, and that's my completeness parameter LC. So I need the text to be large enough to embed a watermark, and this is coming from the fact that I have to embed a full signature there. So the text has to be reasonably long. And we could require similar property about any snippet. So if you took a long enough snippet from originally watermarked text, that should also preserve the watermark. We can say the same thing for similar for distortion freeness, where if I have an attacker D who has access to a model that generates watermark text, or a model that just generates regular LLM text, the attacker D should not be able to distinguish between the two. Here, I want to stress here that in this definition, we're going to have to deviate from the secret key setting in a little bit, because our watermarks are publicly detectable. We are in sort of a distortion freeness. We are in this model where we're not going to let the public key be available to the attacker, because if the public key is available, then one of the two sides is going to have a watermark embedded, and that's publicly detectable, and so the attacker could detect it. Then we have the soundness unforgeability requirement. And remember here, I was saying that the attacker should not be able to come up with new texts which are watermarked. So if I give if the attacker has access to, just like signatures, a list of watermark text T1 to T2 and so on. So think of these message and signature pairs in the digital signature existential unforgeability chosen message attack. So the attacker has access to these watermark texts, and it needs to come up with a new text T star such that it does not overlap on T1 to TL, all the queries, all the watermark tests that see, on any segment of length ls. So the moment it overlaps on a segment of length ls, we are going to, it could potentially be watermarked. But if it's not, then it cannot have the watermark preserved anymore. Okay. And then here the attacker has access to the public key, and it can make these adaptive queries. So there are sort of two requirements here. The ls needs to be large enough, the overlap needs to be large enough. And note that the detection algorithm may not work on very short text. So because of the completeness requirement. So that's an additional requirement. So the text T star that the attacker needs to output needs to be long enough, and it has to have an overlap of length ls with the it has to avoid an overlap of length ls with the queries that the watermark text that it get. Finally, we have another parameter LR for the robustness, where we want to say that the attacker can modify text any way it likes, as long as it leaves apart a continuous segment of length LR. The attacker is not going to be able to remove the watermark. Okay? So it's both a strong and a weak requirement. You can change anything around as you like, but there has to be this LR length segment that's completely untouched. And so that's the robustness requirement. And note here that you can add words and do. And one way to kind of destroy a watermark would be to, let's say, change a word every LR words. So that would not preserve. So that would be one way to destroy our watermark. So, still some limitations, but okay. So what are the main challenges that we face? So sort of the three key challenges were in the secret key setting. We're trying to embed a statistical signal. So, which is very different than embedding a full signature. So you have to have you have to be able to extract the entire signature out of the text to be able to say, oh, okay, here's a watermark text. The detection algorithm has to do that. We can't kind of split the words into red and green and do that. So that's sort of one challenge. The second challenge is, because the watermark is publicly verifiable, you can take a bunch of watermark text and recover various signatures. Right? As I said, we're going to use signatures to embed the watermark. You can use these watermark texts to recover some message signature pairs. If you're able to do that, I can then go ahead and plant them in new message, new strings, which have nothing to do with an LLM generated output, which would make it easy to generate, kind of watermark text. So a key challenge for us is that the signature that gets embedded has to be somehow a function of the message LLM generated output itself. So we have the LLM generating the output, and the signature that gets embedded has to be a function of the output that's getting generated. And like before, we have to handle this low perplexity or low entropy in the text generation as well. The watermarking scheme, as it turns out, is fairly natural. So the idea is, what we're going to do is we're going to generate the first few tokens, let's say the n tokens, without any watermark. So you use your LLM to generate the first n tokens. And then subsequently, you use those n tokens, hash them, extract a message out of it, sign them, and then embed the signature in the subsequent tokens. So you have this list of words that you want to generate. The first few generates are generated not with any embedding in them. So they're actually the source of the message for the signature scheme. And then we use that to sign. We sign that using our secret key and embed the signature itself in the rest of the word. And here we can adopt a strategy similar to prior works in embedding. And just in words here. So we generate the first use the first few words from the model directly, sign them using get the signature, and then we sample the next tokens in a way similar to what the Maryland group did. Okay, so here we would, I'm writing with a hash function, but we would want to use a make it publicly dependent so it achieves the distortion freeness. So the detection algorithm is going to be fairly natural now. So you can take your text and the whatever the tokens you have, extract the message out of the first few tokens, the signature out of the subsequent tokens, check if the signature verifies, and if it does, then you have that. And this achieves. Here we're able to make this dependence in the text from the message itself, because the first few words of the message are what are getting signed and getting embedded. So if you are going to modify, so if entire message signature pair is unmodified, then we're always going to detect it, and that defines our long enough text. If you have an overlap on the message, then you must embed the signature for the watermarking to pass. So that's how we get the robustness properties. Okay, so I'll skip this. Okay, so similar to prior work, we also have a challenge here in terms of handling low entropy text. This is going to be inevitable, just like Barack Obama. There's the example, if you have a text where the next word is clearly predictable. So for example, the largest carnivore of the crustacean period was the Triceratops, and the next word is Rex. So, that's low entropy. It has to be Rex. So if we use our scheme, then we run into this trouble that we're going to have this low entropy, and we're not going to be able to embed signatures just in the way. But we need to still be able to recover all the images, unlike the Maryland group's work, where if there was an error, that didn't really matter because they were working in a statistical test. We have to recover all the images of the signature to be able to get a detection. So instead, we use an error correcting code. So we put an error correcting code that allows us to, whenever we can't handle, we will artificially plant an error, and this allows us to have some even without enough entropy in some regions. We do need entropy for the entire text, but for some region where if we encounter a region of low entropy, then we can get away with planting an error and still being able to recover. Okay, so there are some limitations of our work. So as I mentioned, we have to embed these signatures, and so we need large enough text. So it ends up being around 1,000 tokens, which allows us to embed a BLS signature. So this is roughly 800 words if you're using Mistral 7. It's one of the LLM models. And then a critical limitation is, as I mentioned before, our robustness is only in the setting where this entire segment is completely untouched. So we'll repeat this process, right? So we will embed a message and a signature, message signature. For any text, we keep doing this. If you write a 1,000-page text, but for the watermark to be preserved, you have to have these sort of 800 words that need to be exactly preserved. We did experiments. We did implement it. We implemented both the Christ et al. Scheme and the new scheme that we built out. And it the sort of when our experiments are what motivated us to look at this error corrected version, because when we weren't doing it, the text quality dropped tremendously. But with this error correction, the text is of it looks reasonable. It would be indistinguishable. We can prove that as well. So okay, where do we go from here? So let me try to conclude. The takeaway is, achieving robustness is really difficult or unachievable, as we saw in the impossibility work. And I think that given all these laws and really the harms that are coming in, a lot more thought needs to go into developing these watermarking schemes. We don't have clear understanding of the applications and what properties are going to be essential. There are cases where reasonable, legitimate cases where actually robustness is, we cryptographers often kind of get excited about attackers who have all the power, but there are settings where attackers don't really have an incentive to or are interested in setting where there are applications where people care, where it's not relevant whether the attacker modified text or not. So for example, when OpenAI is training new models, they are collecting data from the internet, and they don't want to train their model on the data that they had generated themselves with the prior model. So this is a problem for them. So they want to embed watermarks to make it easier for them to detect that this was not generated by us. Now, of course, maybe people, some student might change their essay a little bit here and there, and that might destroy the watermark. But they're very much interested in maybe legitimate use cases where everybody's just doing everything legitimately and so on. They just don't want to, or at least minimize the amount of stuff they retrain their models on. So that there, at least I can weed out those cases where the watermark, someone hasn't actively tried to remove them. But the moment we say that, oh, okay, attackers are allowed to make changes, well, where do we draw the line? How much changes are reasonable? How much is too much in developing watermarking schemes for them? I think in our context, and what we focused on with the public key setting, forgery is actually quite damaging. So maybe this is sort of the opposite, that maybe I'm less interested in the setting where people can remove the watermark, but I don't want people coming to me and saying that your model is liable for generating hate speech or something like that in a court of law. And so this is where I think public watermarking could be useful. So yeah, that's all I had. Happy to take questions.
Any questions? You want to come up on here and then, or project your voice. Let's channel our innocent child.
If the output of the large language model is very specific, such as an image or tabular data, then can you do something better that does not have the long lenses?
So as I mentioned, we are focusing only on text. And as I mentioned, if you use error correction, the moment if you expect places of low entropy, you could embed the signature in a longer text. And so, if you have maybe a tabular form, as you mentioned, and so part of the things are going to be fixed, then at those places you could artificially plant errors if you need to, as long as from the entire text segment you can recover. Yeah, but maybe I'm not sure if I got the question. But you will have to increase the length of the overall text that should not be modified.
What's like the distance usually for like how you consider if something's being perturbed? Is it just something like timing distance, or like reduce that? Like, and then for like machine learning, there's like more advanced like semantic kind of distance measures and stuff like this.
Yeah, in this work, we're working with exact sequence. There are other works. I mean, I think Miranda also has a newer work, and there's a work I cited from MIT, where they're looking at edit distance as well. So there are different measures. And again, very good questions. What is reasonable for an application? The laws don't really provide a clear guidance on that. And so it's very relevant to understand the applications. And yeah.
That's the question. Yeah, go ahead.
I wanted to ask about the assumption about, so in this line of work, it seems like we're not going to bother like messing with the training process. I wonder where that assumption comes from. Like, is that a hard requirement? Is OpenAI or whoever saying, I don't want to mess with the way I do training? I'm curious if like, if we open up that possibility, could we do more?
Let me answer the second question first. That's easier for me to answer. Because I'm not sure what more we could do. Because it's not like we understand how those models work anyway. The first, in terms of opening them up and changing, I'm actually not sure. So where does that assumption come from? That assumption does come from, I think, the prior work to some extent, where it seems natural to separate the crypto part, where you're embedding the watermark, from I'm not sure how you would embed a key inside like if you were using, I think in that case you would go in this sort of the first line of work that I was mentioning, where you're perturbing the model a little bit to change the distribution of the output to not look like the best it can. But then that's not ideal either for the model. The model is trying to generate as humanly similar content as possible, right? Now, the moment you bring the crypto out, I think it's a clean interface. You can say, okay, this is the part we're going to do. There could be some efficiency optimizations, right? We have some rejection sampling that needs to be done. in the prediction. So once you pick the next token, if it's not the red one, you pick a new one and so on. So that's not ideal. That adds some computational time. There could be some efficiency gains, but I'm not sure what you could also gain by going inside. I don't have an answer. Yeah, good question. Thank you.
Let's find the speaker again. So while we get set up, we have a few minutes free though, so you'll have the LLM session now.